The case where the filter is symmetric, you know, I can always group like this, and I have something out here. So one thing for sure is something here is linear. This is a linear phase. But if this thing here is still negative, I cannot guarantee that it have a linear phase, but this has something else. Okay. Maybe I show an example. And then I can talk. So, for example, if I have an edge of omega equal to A omega times Ej theta omega. So maybe let's plot it out here. Let me just draw the thing from 0 to pi. 0 to pi. Okay. And for example, the A here, those A. Let's say the A coming something like this. Something like this. So that's the A. So there is the A of omega. Okay. And here is the theta of omega. That's the theta omega. So now when I have to convert this thing now to the complex, to find out the magnitude and the phase of that, then the magnitude of this would be this function, and then I take the absolute value of it would be this. So this would be the edge of omega magnitude, right? In the range of this thing here, positive, I just have to take that, but it's negative, I have to take the negative part of it. Now, for that the case, and the phase of this, so let's call this thing here is a pi over 2. So the pi over 2 here, this thing here, what happened? I have this thing here going down here, and then all of a sudden, it jumped up here. You're going to add by pi. And then it goes down here. So that would be the phase of H omega. Okay? So what people would call here is this is a pi jump on the phase. This is a pi jump. And where do we have that jump? Where do we have that jump? Where this thing goes across 0. So only jump when H omega equal to 0. The magnitude of this equal to 0. Right? Is that clear? Alright, so this jump, but this jump actually is daily jump because I thought I originally have a linear phase like this. Everything delayed, by the amount set. But all of a sudden, it did the thing, then it destroyed the linear phase that we have. You agree, right? So this is not a linear phase filter. It's not a linear phase filter. But in that case, and this filter, the filter having that form, where, let me repeat, this is real, and this part here is real. The only difference is real, but still can be negative. Where this thing here is real and non-negative. Right? The only two different. But the filter having that general form, where if I have a theta of omega equal to some alpha times omega, if I have this, is called generalized linear phase. Okay, GLP. Okay, so you see the GLP is the generalized version, but it's as good as a linear phase. Right? It's as good as a linear phase for the practical purpose. And in the homework exercise, we're going to generalize that because you can imagine now, if any symmetric filter, you can put in that form by just grouping the terms, symmetric terms, right? You get something real, out, and you can put that. Okay, is that concept clear, everybody? We now want to look into how could we design a filter that meets a certain requirement. Right? So that is the topic, the last topic of today's lecture, is the filter design. Filter design. Alright, so that is the filter design topic here. Let's take a simple case. Take a simple case here. Someone come and tell you, okay, I have this signal coming in, and in the discrete domain, and I really want, so from 0 to pi here, I want all the signal from from minus omega naught to omega naught to go through, and anything else I want it to filter to reject it, right? So that is an ideal filter. So suppose that someone asks you to design a filter like this. So filter they with the requirement, right? So you can imagine the requirement. Let's say you play music and you want to turn the knob and you only want to get that really low beat, like boom boom boom, where all these things get rejected. Okay, so you want to design that filter. And the question I have also in mind is, I want to design a filter that I can instruct someone to design a circuit or a computer program to run it for me, right? So that's the message. So this is, let's say, it is an ideal filter. So the SD omega is the desired filter. The filter that I really want, right? The filter that I really want. So I say, okay, if I have that filter, not a big problem. Let me take the inverse DFT, inverse DTFT, and see what that coefficient look like. And then I tell you to do the convolution, right? So that's the first part. So you take that, and now you want to do the inverse. So you have this Hn of the desired filter. What that would be? A sinc function, right? Anyone remember what that sinc would look like? Sine of maybe omega naught n over omega naught n. Maybe. I'm not sure, but okay, let's assume that. There may be some term here. I don't need to check it, right? But like my story, my message I want to have. What happened with that filter? What is the problem with that filter? It's gone forever, right? Because the same function, as you know, is going to wiggle, even though it's going to die, but it's going forever, and you have a sample here. So you cannot tell someone to take that filter to compute, right? Because you know that if you have to compute this, I have to compute yn equal to summation in x in hk x of n minus k, and I have k go from minus infinity to plus infinity. We say, okay, take that, put in that formula, compute it, no problem. Oh, no. Computer cannot do that, right? So you have to do something. So what should we do?